Understanding electromagnetic pulse effects, infrastructure resilience and protection. The growing reliance on electronic systems in modern society has sparked increased attention to electromagnetic pulse, EMP phenomena, and their potential effects on critical infrastructure. This article examines the scientific principles behind EMPs, their impact on electrical systems, and the ongoing efforts to protect vital infrastructure. The science behind electromagnetic pulses. An electromagnetic pulse is a brief burst of electromagnetic energy that can disrupt or damage electronic equipment. The phenomenon was first observed during high-altitude nuclear tests in the 1960s, when streetlights in Hawaii were affected by a test hundreds of miles away. This discovery led to decades of research into both the physics of EMPs and methods of protecting against them. The mechanism behind EMPs involves the interaction between charged particles and the Earth's magnetic field. When a nuclear detonation occurs at high altitude, it releases gamma radiation that ionizes the surrounding air molecules. These ionized particles interact with the planet's magnetic field, creating a powerful electromagnetic field that can induce electrical currents in conductors below. Modern infrastructure vulnerability. Today's society depends heavily on electronic systems for everything from communications and banking to healthcare and transportation. The miniaturization of electronics, while bringing numerous benefits, has also increased their sensitivity to electromagnetic interference. Modern integrated circuits operate at such low voltages that even relatively weak electromagnetic pulses can potentially disrupt their function. The interconnected nature of critical infrastructure systems creates additional vulnerabilities. The power grid, telecommunications networks, and digital control systems are all interdependent. A disruption in one sector can cascade through others, potentially amplifying the initial effects. Understanding these interdependencies is crucial for developing effective protection strategies. Critical infrastructure protection. Engineers and policymakers have developed various approaches to protect critical infrastructure from electromagnetic effects. These include both physical shielding methods and operational procedures. Faraday cages, metallic enclosures that block electromagnetic fields, protect sensitive equipment in many critical facilities. Surge suppressors and specialized grounding systems provide additional layers of protection. The defense industry has led many developments in EMP protection, as military equipment must operate reliably under adverse conditions. These hardening techniques are increasingly being adapted for civilian infrastructure. Modern data centers, for instance, often incorporate electromagnetic shielding in their design. Government agencies have also taken steps to assess and improve infrastructure resilience. The Federal Energy Regulatory Commission, FERC, has established guidelines for protecting the power grid from electromagnetic disturbances. These include requirements for vulnerability assessments and the implementation of protective measures at key facilities. The role of testing and standards. Ensuring infrastructure resilience requires rigorous testing and clear standards. Organizations like the IEEE have developed testing protocols to verify the effectiveness of EMP protection measures. These standards help manufacturers design resistant equipment and allow operators to assess their system's vulnerability. Testing facilities create controlled electromagnetic environments to evaluate protection methods and equipment durability. These tests simulate various electromagnetic disturbances, helping researchers understand how different systems respond and identify effective protection strategies. International cooperation and research. The global nature of modern infrastructure networks has led to increased international cooperation in studying electromagnetic effects and developing protective measures. Research institutions worldwide share data and expertise, working to improve understanding of these phenomena and develop more effective protection methods. This cooperation extends to space weather monitoring, as naturally occurring solar events can create similar electromagnetic disturbances. Organizations like NOAA's Space Weather Prediction Center provide early warnings of solar activity that could affect Earth's electromagnetic environment. Future challenges and opportunities. As technology continues to evolve, both vulnerabilities and protection methods will change. The increasing adoption of renewable energy sources and smart grid technologies creates new considerations for electromagnetic protection. However, these developments also offer opportunities to build resilience into systems from the ground up. Emerging technologies like quantum sensors may provide new ways to detect and characterize electromagnetic disturbances. Advanced materials research is yielding new shielding options that are more effective and easier to implement than traditional methods. Public awareness and preparedness. While much attention focuses on large-scale infrastructure, individual preparedness also plays a role in societal resilience. Understanding basic electromagnetic protection principles helps organizations and individuals make informed decisions about protecting sensitive equipment. Educational initiatives help professionals in various fields understand electromagnetic risks and protection methods relevant to their work. This knowledge enables better decision-making about system design and operational procedures. Economic considerations. Implementing comprehensive electromagnetic protection measures requires significant investment. However, the potential costs of infrastructure disruption far exceed protection expenses. Risk assessment frameworks help organizations balance protection costs against potential vulnerabilities. The insurance industry increasingly considers electromagnetic risks when evaluating infrastructure systems. This has led to more detailed analysis of vulnerability factors and protection methods, helping organizations make informed decisions about protection investments. Regulatory framework. Government agencies continue to refine regulations regarding electromagnetic protection of critical infrastructure. These regulations set minimum standards while allowing flexibility in implementation methods. Regular review and updates ensure standards keep pace with technological changes and emerging threats. Conclusion. Understanding and protecting against electromagnetic effects requires ongoing effort from multiple sectors of society. Success depends on combining technical expertise, operational procedures, and policy frameworks. As technology continues to advance, maintaining infrastructure resilience will remain a crucial challenge, requiring continued attention and investment. The path forward. Developing effective protection against electromagnetic effects requires a balanced approach that considers both technical and practical factors. This includes continuing research into electromagnetic effects and protection methods, implementing cost-effective protection measures for critical infrastructure, maintaining international cooperation in monitoring and protection efforts, developing workforce expertise in electromagnetic protection, regularly updating standards and regulations to address emerging challenges. By maintaining focus on these areas, society can continue to enjoy the benefits of modern technology while ensuring critical systems remain reliable under adverse conditions. The ongoing work of scientists, engineers, and policymakers provides a foundation for addressing future challenges in this important field.